Okay, good. So, welcome everybody. That's the first lecture, and the first thing I'm going to do is to give an overview on what this class is about, what we do, how we manage the whole semester together, and introduce the TAs and explain a bit practical information. After that, I will give an introduction to the class, but more formal, in terms of what are the problems that we are going to address, what we study, how we handle it, and so on. So, first of all, the topics of this lecture is a very long list, and it's mainly about mapping and also localization, because the two problems are actually interconnected. So you will see this thing here, which is simultaneous localization and mapping, which will be like the core, the big container of everything that we will address in this lecture. And here there is a list of potential way of addressing this problem from an estimation point of view. So we get the data, how we can handle this amount of data, how we can get some structure, some model out of the data that we collect, and plus some more advanced things in the end. So the first part here is more like the history, when the whole problem started, and we go step by step in increasing difficulties, more complex problems, more advanced techniques. The spirit of this class is to give you an introduction to this problem. So the goal is not to give you the state of the art, the latest development, but more like a knowledge on what the problem is, how it's been solved during the time, so you can get these building stones, and then you will be ready to approach the more advanced techniques towards the end, or if you want to do a master thesis, or if you want to continue on a PhD level, then you know the basics on how to address it. This was a very key problem in the past 20 years. If you think about robotics, and especially mobile robotics, you imagine that the robot has to navigate somewhere, and the somewhere has to be modeled in some way. And this problem is in how to model this somewhere, how to model the environment. There have been a lot of relevant state-of-the-art approaches that we will describe later on. And during the exercise, we're trying to do something a bit practical. So you will have octave codes, and you will have some exercise so to solve some simpler mapping problem, and you will do it on your own using Octave, and try to get also coding experience on how to estimate, how to model, how to build models of the environment. Okay. So what do you need for this? First of all, you need some mathematical skills. You need to know something about linear algebra, so how to handle vectors, matrices. You need to know also some concept about gradients, derivatives, partial derivatives, and all these numerical tools for dealing with vector spaces. You need some probabilistic concepts, so you need to know what the distribution is, how to handle distribution, how to do probabilistic filtering, how to do information fusion, and so on. Many of these skills you had. So in some way you should have gotten them if you attended the Intro to Mobile Robotics. So you can see this class as something that can build on top of Introduction to Mobile Robotics. That class was about a broader spectrum of mobile robotics problem, and here we just focus on one specific aspect of that. Okay, but the main basic tools will be roughly the same, and some of the concepts might sound familiar for some of you that attended that class, and it's actually a good thing because you will have the time to deepen the knowledge on that and to build on top of this. The exam will be oral, as it was also for Intro to Mobile Robotics, so we'll just have a 25-minute discussion with me, and we'll talk about things. I'll ask you questions, you'll answer them. Be happy if you give a good answer, and then you get a good grade. So that's somehow how it's going to work. Just to get an idea, how many of you have attended the Intro to Mobile Robotics? Okay, so many, not all. So I have to go somehow a bit slower on a few of the concepts. But it shouldn't be a problem. So you should be able to catch up quite soon on, on the topics of Intro to Mobile Robotics. So more practically, the class will be on Monday. I will give you like a, let's say, theoretical lecture on the topics. And on Thursday, there will be the exercise session. Now, the idea of the exercise session is you will have exercise every week. You are supposed to do them at home on your own. And then on Thursday, the TA will give you the solution and will explain you how to do the exercise. The two TAs are in the back line. You can maybe stand up and the people sees you. So if you want, you can introduce yourself. Mm-hmm. Mm-hmm.
Hi, my name is Noha. I'm a PhD student at the AI Systeme.
Yeah, and I'm Alex, and I'm also a PhD student. And I'm just
the first exercise session will be slightly different because you don't have any exercise to bring. So the idea is I'll give you an introduction on homogeneous coordinates and transformation. That's something that we will use later on in the class to deal with orientation and translation. And then there will be a Octave exercise, which basically means we'll try to install Octave to all your PC if you don't have it, and set up the whole environment so that you are ready to do the exercise. So if you have a laptop, it's a good idea to bring it with you on Thursday, so that we make sure that everything is working, all the materials of the exercise are working, and there will be a bit of a crash course on Octave, how to use it and how to handle it. If you're already good with Octave, you know everything, you can also not come, but I recommend you to do it. So exactly, so that's what we're gonna do in there. Besides the lectures and exercise, there is also some, let's say, tools that you can use for this class. We have a Google group, and the link is on the web page of the class. I don't know, how many of you have seen the web page already? Okay, few of them. There will be all the slides, the PDF. I'll try to make the PDF available before the lectures. It's not always possible, but I'm trying my best. And we'll put also the recordings there, either there or on YouTube, but you will have anyway a link on the web page for the recordings. The Google group, I'm using the same one of last year, so just to not create an infinite number of Google groups and not using them any longer. If you want to have your own one, your personal one, I can make another Google group just for this year. Just let me know. There is no forum, and I think the group should be good enough, but if you want to have whatever other tool, let me know. I'll try to make something for you. Regarding the emails, you can write me an email if you have any question about the lecture. If you have any question about the exercises, it's better if you email directly the tutor, because they might know even better than me how the exercises are made, or let's say the technicality behind them. The material is, of course, the slides of the class, the recordings, and there are, on the web page, there are a list of additional material that are research papers, lecture notes, technical reports, and so on. You have a complete list of that, and in each lecture, I'm trying to give pointers to which additional material is useful for the specific lecture. If you like books, that's again the main book where we base also this class. Part of especially the last part of the lectures is not covered in the book, because the book covers more the basics of probabilistic robotics, but the initial part, let's say the first 2/3 of these lectures are fully covered there, and the more we go on, there's more, like say, novel material. So some of the things I will teach you are younger than the book, so that's why we couldn't put them in there. Yeah, so if you have any feedback, if there is something that you don't like, let me know. If there is something that you like, also let me know, because it's always good to know if something is working or not. And of course, it's better to give feedback as early as possible. It's not nice if you were just suffering during the whole lectures, and then at the end, during the exam, you come to me and says, yes, but the lecture was not good. That's a bit too late. So if you give feedback in the early stage of the class, then I can try to change, improve, whatever you want. Okay? Now, do you have questions for me? Yes?
Can you please introduce yourself?
Ah, okay. That's actually a good point. So I'm Diego Di Paldi, and I'm, let's say, to translate in English is probably a lecturer in the S Lab, and I'm giving you the class. I worked in the last 10 years on localization and mapping problems from a research point of view. Okay, good question. Something else? Someone else? Okay. Yeah, so that's that concludes the bureaucratic administrative part of the today lecture, and we can then go to the more fun part, which is the bit more of theoretical meat on this. So we might finish a bit earlier today. So this is was planned of having more these questions from you, so to give some space in there. Also, another thing which I wanted to ask you guys, these are 2 hours lectures. It's planned to be anyway 45 minutes continuum lecturing. So we can also for the future have a 15 minutes break at the end of the first hour, or we can finish 15 minutes earlier. Some students prefer finishing 15 minutes earlier, some other prefers a break in between. What will be your preferences?
Break in between.
Break in between. Okay. I'll keep it in mind. Sometimes, I mean, let's say if there is something that I need 10 minutes to finish an argument, we may switch the break a bit later on. But I'll try to make then the break in between. Yes?
Sir, I have a question that in this course, will we work on the ROS and the planning stuff, or what will be the environment we will be working on?
So there is no, there will be no real active part in this class. So we are not gonna plan a path for the robots, and we are not gonna have the robot navigate anywhere. What I'm gonna teach you is basic techniques to address mapping and localization problems independently on how you want to implement them. And to make things easier so that you don't have to learn the full ROS if you don't know it, we do the exercise in Octave. So it will be just like MATLAB style scripts. If you're interested in ROS, we can talk offline on how other things, but in principle, whatever you learn here, you can, and whatever you during the exercise do in MATLAB, you can take it, convert it into C++, add some ROS interfaces, and you can work in ROS in principle. So yeah, it's more on the basic thing rather than on a specific library for doing stuff. Okay? All right. So robot mapping. The first thing to say is basically what is robot mapping. And we know what the robot is. No? So a robot, you can define it as a device, a system, or a box, if you want to put it very, very abstract level, that can move through the environment. And in principle, it's defined as something that can sense things from the environment, can reason about that, and can act accordingly. And the mobile robot is a special robot whose only action is to move around, basically. And mapping, we use it somehow improper, the English word, but actually means modeling the environment. So in informal way, it basically means to build a map of the environment. Okay? There are a few other terms that you might see around. So mapping is what we've seen. SLAM is what we said before, stands for simultaneous localization and mapping. Of course, we have localization, which is just the problem of knowing where the robot is in an environment. There is also this other related term, which is state estimation. And state estimation is a big container on system theory and robotics, which basically means I have a system. The system has a state, and the state can be like the position of something in the world, its velocity, its acceleration. Can be, if you have a manipulator, the angle of each joints of the manipulator. So something that define a system. Okay, and these states can evolve over time and so on. And state estimation is the problem of getting sensor data. What is the state of my current system at a certain point in time? If you look at mapping or SLAM or localization, basically this is also a state estimation problem. Our state is the position and the orientation of the robot over time. It evolves according to the encoder that we have in the wheels, and you get some measurements out of either cameras or sonars or laser scanners. And the localization problem is a problem of estimating the state of the system when the state is the position and orientation. If you go to mapping, it will be estimate the state of the system where the state is the environment representation. And if we go in SLAM, is both the environment representation and the position of the robot. Other related terms are navigation and motion planning. We are not going to deal with these two parts in this class, but you might imagine that for doing motion planning and navigation, you need to have a map, because you need to have a way of knowing how I can reach a certain part of the environment, given that I'm somewhere else. And if I have, for instance, if I'm here and I want to go outside of this building, I need somehow a map of this room, because I need to know how to exit this room to get the door. I need a map of the building, because I need to know that I have to go down the staircase to exit the building, and so on. If I have no idea of the environment and someone just tells me you have to go out, I might just go jump out of the window, no? Because I'm just trying to go on the direct line to reach a goal. So planning and navigation are, they need somehow a way of knowing the connectivity of the environment, so they need to have a representation how the environment looks like, it's connected, and so on. Okay, so that's just to give you an overview on the bigger picture of how this class fits into robotics in general. So what is then the specific problem that we are addressing here? What is the SLAM problem? As I said before, this is defined as computing the robot's poses and the map of the environment at the same time. So you can imagine that you bring the robot here, you turn it on, it knows nothing, and it goes around and tries to figure out where he is and at the same time how the environments look like. Okay? Now, if you take these two problems, localization and mapping, they are kind of easy or easier if you take them separately. So if you assume that you know where the robot is, you can imagine that for building a map, you can just take the sensor data and accumulate one on top of each other, no? Because you know exactly where you are, you just care about how the things that I'm looking fits together. If you have a map, then you can try to just fit your current data to the map and try to realize where you are. So when you deal just with the localization problem. When you do SLAM, so when you treat the two things together, you have kind of observability problem in some sense, because you don't know if now an error or a measurement noise is exactly a noise, is a mistake in the map you built so far, or it means that you are not where you thought but you have to be somewhere else, no? Because there is no prior knowledge neither of you of where you are or where the environment looks like. If you want to see it graphically by some examples, so imagine that this will be the ideal world. Our environment is made of stars, so we are like a ship in the ocean, so we just look at the stars and we try to see how our features look like. And if everything is perfect, we just go from here, we go around, we see the stars from different locations, and our measurements are perfect, so we always see the star in the exact specific location. Now, if we are trying to localize, what actually happens is that nothing is really certain. So we try to move around, we think that we moved here on the left, but in reality we are here. And what we try to do is like, okay, let's observe a landmark. I should have seen a star here, but there is no star. But I see a star here, so this difference here tells me, okay, I need to maybe adjust my location because I'm wrong. okay? And the same go on. So you do here, you do a bit of adjustment in this line, then you go again forward, and you see that there is another misalignment of your sensor readings, and then you try to adjust a bit backwards there, okay? But the stars are fixed, they're in the sky, you know exactly where they are, and everything is easier in this sense. If we just want to do mapping, what happens is the other way around. Again, this is our path, this very nice ideal world, but what happens is when I'm here, we don't know where the stars are, and we just have an observation of the stars. So at this point, we have no other measures, so we can just trust our observation. We believe a star is here, but actually it should be a bit further away. Then we go forward, but we know that our location is perfect because we're just doing mapping, so we know exactly the location of the robot in the environment. And then we do another observation, we see a star here, then we move it again, we see again this star here. And if there is a mismatch between these two observations, we can use it to adjust the location of the stars in the world, okay? But again, this location of the robots makes it quite easier because we can at least rely on something, which is the location of the robot. If we do SLAM, we actually have problems, or let's say measurement errors coming from both aspects. So we have some location error, as we've seen before for the localization, but we also have some map error because we don't know the map beforehand. So you can see here that differently than before, when we were doing localization, I could use this information that the star was here to adjust my pose and go a bit down here. But in this case, I have no information about that. So the only thing I can do is I can trust my measurement up to here. I can put a star here because that's what I'm observing. And then I hope that I will go around the star multiple times to somehow reduce the uncertainty in the pose and the uncertainty in the location of the landmarks. This seems a bit maybe too complex for now, but you will see later on how this whole idea of adjusting the stars and the location of the robot will come easier when we explain you how you can do it and what are the tools around. Okay, so is there any questions so far? So another thing is you can interrupt me anytime. You can just raise hand and ask me a question. So I find it quite useful also for the students to be a bit interactive in the lecture, not just me telling you something. Getting back to why the SLAM is actually a hard problem, some people define it as a chicken and egg problem. And by chicken and egg, it's this philosophical question that what was created before, or how evolution actually came to the chicken idea or the egg idea before, and what's the whole kind of loop. Because once you are in a stable system, you just see the cycle, but it's hard to imagine what came first. No, so that's the idea of the chicken and egg. And the same you can imagine for localization and mapping, because normally you would like to have a map for doing localization, and you also would like to have a post estimate to compute a map. Okay, so that's where these things come from. And as you can imagine, this can create a loop, and exactly one way of addressing this problem is to first estimate your location with a map that you have estimated before in the previous time step, and then you try to re-estimate the map, and then you try to relocalize and re-estimate the map, and so on. So to get a convergence to a unique solution at some point. And why is this problem relevant for robotics? It is actually one of the most fundamental problems if you want to have a robot moving around. The reason is that this is the basis for most navigation systems. So if you want to do, if you want to be autonomous, if you want a robot to be able to make decision on its own, it needs to have enough information for making a reasonable decision. Okay, and this enough information is, for instance, where are the obstacles in the environment, how I can connect different places in the environment, and so on. And for doing this, you need to build a representation for this connectivity representation, which can be either given by a human, but then you remove a part of the autonomy in the system, because you always need some user with some good knowledge of how the whole navigation system works, such that it can create a meaningful representation. Or you can give the robot tools to be able to build his own the representation on his own, okay? And that's where the SLAM comes into play. Application of SLAMs are numerous, but you can imagine every time you want to have a robot moving on its own, you need to have something like SLAM or similar implemented there. Potential example are like vacuum cleaners or lawn mowers. So I guess many of you know like Roomba or Miato or any of these intelligent vacuum cleaners. Some of them have somehow a SLAM algorithm implemented in their small control boards, okay? So they kind of build a map of the environment based on some data that they can collect. And then they use this map to know where they've been cleaning and where they've not been cleaning and which part of the environment needs more cleaning than something else, okay? Same thing for lawn mowers. If you want to cut the grass in your lawn, then you need to know where the grass is, you need to know where are the roses that you're not allowed to go there because actually you want to keep them, and so on. You also have to be aware of the cat and stuff like that. Similar, if you can go on air, you can do surveillance, or you can also do pictures or videos. There is now a lot of these drones that are flying around with cameras that they can make videos of you while you do crazy sport actions. Well, all of them somehow have a kind of SLAM inside. They need to know where they are with respect, for instance, the base station, no? Because at some point they need to fly back and recharge themselves. And they need to be able to localize themselves while they're flying. And you can imagine if you have a map, you can also design a path that you have to follow to have a nice view over the concert that you're trying to film or whatever, no? So all of them might have some SLAM algorithm implemented in them. You can also have some underwater and underground applications, like you want to monitor some reef, some coral reef underground, and you want to build a map of the reef so that you can bring this map back to marine scientists, and they can analyze the state of the corals, if they're alive, if they're dying, if there is something that they need to do there, and so on. And say, similarly, if you want to explore mines or catacombs or anything that requires building a environmental reconstruction of that, and also which is not easy to perform from a human point of view, no? Because these mines might be poisonous, there might be some gases there, and same for the reef, it might be too deep to dive there. There's also some space applications where these rovers are sent to Mars and they're trying to build a 3D reconstruction of the surface of the planet and send it back. They need to use some SLAM technique for doing that, okay? So in terms of typical robots, that's how they might look like. This is a kind of a vacuum cleaner. It's not really a vacuum cleaner. It's called Mint. It's just using a sweeper to remove dust. So it just removes dust from the ground, but it doesn't really suck it in, but it just takes a static draft and it removes the dust in this way. Here you can see a typical underwater robot. So it's made, like there is a cage here for the sensor. There is a tube here, which is the main body of the vehicle, and there are some other sensors on top here, some cameras, and so on. You can see here a typical space rover that is building a reconstruction of the planet there. This is the moon, actually, and here is the Earth, just to give you an idea where we are there. This is a typical underground mining robot, where there is a lot of mud. It's very hard for a human to go there, so they just send a robot. You can see also a cable here. That's because wireless communication in the mine doesn't really work when you are outside, so you need to have some way of communicating with the robot from the outside. Now, to get another idea of SLAM in action, here is a video of this Mint, this, let's say, vacuum cleaner. And what it does is he has this cube. You put it on top of a table. It projects some stars on the sky, which basically now is the ceiling of your room. And then the robot goes around and observes these stars. So he builds a map of the star of the ceiling, and he basically knows where he is and where he cleaned beforehand. And he uses this to know if he has to go twice on top of some part of the environment, if he misses something during the exploration, and so on. He also uses some other sensors, like touch sensor, to know if there are obstacles. So he puts these obstacles in the map he creates, so that he knows that he cannot go over that. But basically, the idea is that through this sensor here, which is a camera pointing up, is able to build a map of this point constellation of the ceiling and localize. They have more advanced version of this. This is something like 4 or 5 years ago, maybe, or maybe 4 years ago. It's been first prototype coming out. Now they have fancier intelligent vacuum cleaner, but the principle behind to build the map of the environment is still valid. Another showcase here is a project that we had in our lab. It's called Europa, where we move, we navigate autonomously from here, the campus, to downtown Freiburg. And for doing this, we had to build a map of the environment. So this is the robot that we were using. And what we did here is, during the preparation phase of this project, we drove the robot from here to downtown and measuring different possible paths, and we built then a map of the city that kind of contained many of the streets and many of the part of the environment from here to downtown Freiburg. So we didn't build the map of the full Freiburg, because for that project we only needed to go from here to the end as a showcase, but in principle the same technology would have been used to just build the full map of Freiburg. And the map was looking something like I will show right now. That's like an extract of how we build it from this campus here. You can see here a zoom up, and there is a larger part of the environment. This part here is the sensor we used. So we used the laser scanner, which is a sensor that measures the distance of the closest obstacle from the robot, and it does a swipe like this, and this is the area that has been swept. And you can see here is the path of the robot. This thing here is the robot, and then you will see some black dots, which are the obstacles that the observing during the mapping phase. So you can see here it's moving around and it's starting to build a representation of the environment. It goes around, and at some point it tries to come back and is accumulating some errors. So you see the things do not overlap. But then it tries to align these things, and once he finds a good overlap, then this uncertainty in where the stars are actually is decreased, because it's using observation from multiple sources, and is able to then build a consistent representation of the campus here. So just to give you an idea of the scale, we are here in this building, in the room up here on this floor here. That's the Mensa building. That's our lab where we are located. Here, down here is the parking lot, and here will be the 101 building, which was not included in the map. So, and that we did it by just a robot, a 2D laser scanner, moving it around in this campus here. Okay? So that's somehow very abstract, but let's now try to go there a bit more into the mathematics of the problem itself. So we're going to start to give a bit of notation here. We consider normally U as the control given to the robot. So in this case, this, for instance, could be something like go forward 3 meters, rotate 2 degrees, or it can also be in terms of velocities, or like go on with this velocity, translational or rotational, or can also be like a set of coordinates in a different frame if you have odometry. We'll see in detail how to express this part, but in principle it's an information that is relative from the robot, and it doesn't use anything which is outside. So it doesn't observe the environment, but it only observes the state of the robot, and is used to know I'm here, I do an increment, which is my control, and now I will be here. Okay? And the problem is if we have some noise in this part of information, this noise accumulates over time. So if you just propagate and just say, okay, let's just try to estimate the location of the robot by just accumulating these relative motions, these relative commands, we will end up that eventually very far away from where we actually are. Therefore, we need some external observations, which we call Z, which are observations of the environment. So we use this to actually anchor ourselves within the environment to know where the robot is. And we also use them to build a model of the environment. Okay, so these are the observations that can come from a camera. So like we can measure color or intensity if it's a black and white camera. Or if they come from a laser, we can measure the distance and the angle of individual obstacles in front of us. Okay? And what we want is a map of the environment, which we just call M. And this map can have different representation that we will see later on. It can be a set of stars, it can be a set of very fine points, 3D points, or it can be like a grid with cells saying it's free or occupied, or so on. And we also want to know the path of the robot. Okay, so we don't know the path of the robot, and therefore this is again SLAM, so localization, which will be this part here, and mapping, which will be this part here. Okay? Now, we are going to use a probabilistic approach for doing this, and this basically means that we are going to model uncertainties in both robot motions and observations, and then we will use probability theories and specifically bias rules and bias theorem and the bias filter to represent and model and filter this uncertainty over time. The idea basically is, instead of saying the robot is exactly here on this location, we will say that the robot is somewhere around here, and this, which is called PDF, is a probability density function. It tells you what's the probability that the robot is in a certain part of the environment. And for doing this, we just take, let's say, the integral of this function from this and this, and we say the probability of finding the robot between x3 and x5 is 85%, and something like that. Okay? So we'll never be able to give you an exact location, but we can say, I believe the robot is here with a certain probability and or a certain variance of where it can be, or so on. Okay? Any question? So if we then put the whole problem, all the notations we had and all the probabilistic interpretation of this, we have that we want to estimate the robot pose and path and map. So we want to find the density, so this distribution here, of the robot trajectory and the map, given that we have a sequence of observations and a sequence of controls. So this basically means that this is our prior knowledge, what we observe, what we can measure, what we have, and this is the unknown variables that we are trying to estimate. Okay? Again, this is a state estimation problem. The path and the map are the variables that are in our state, and the Z and U are the observation, the measurements that we collect over time. Okay? The indices here are just time, so discrete time indices, because most of the sensors come with a certain clock, so you get measurements at a certain frequency, like 10 Hertz, 50 Hertz, or so on. Therefore, we have a discrete indices here. If you, by mistake, or not by mistake, but if you by chance have continuous signals, then this will be something like, instead of a sequence of variables, will be a process, or will be a function which is stochastic. But in this case, we just consider discrete indices, okay? And for simplicity, we just assume that all the sensors, so the external one and the internal one, have the same clock and come at the same discrete time, okay? This here is what also is called full SLAM problem. There are also some variants. So another variant is called the online SLAM. And the idea of the online SLAM is you're only interested in the current pose of the robot and the map. but you don't care where the robot was in the past. And for estimating this, you can imagine that you go through this distribution, so you try to estimate the full path, and then you just forget where the robot was in the past. Okay? It's not as trivial as this, because in this case you might use future location or future measurements to get an estimate of previous poses, and in this case you just forget them. So you just commit on a location in the past and you cannot revise that. So in some way this is more powerful, but it might be more expensive, and this is less powerful but might be less expensive. In some specific cases there is a way, there is a, let's say, equality for this two, in case you just consider the last pose here and the last pose here, but that's just if the system is linear, everything is Gaussian and so on, which is something we'll see later on. If you see it from a graphical model point of view, how many of you know what this kind of diagram means and how it does look like? 1, 2, 3, 4, 5, 6. Some of you. Okay, so this is a way of expressing independence between random variables. Okay, so each variable we have here, so the controls and the previous time step, the observations, the map, the state, the pose of the robot, and so on. These you can always all see as random variables. Okay, so a random variable is a variable that doesn't have one value, like deterministic variable, but it's a variable whose value has certain probability of being within some ranges. Now, what we've seen before with the robot is not here, but is somewhere around this part. Okay. Now, whenever you have random variables and you have a lot of them, you need to consider independence between them. Independence means that if I know something about variable A, and then I want to know something about variable B, and those two are independent, it means that the information of A doesn't say me anything about information on B. Okay? And this is important because you can eliminate part of the computation, because you can just say, this gives me no information, I just don't consider it. And you make the problem a bit easier in this sense. And it's also important to then reason on this model to get an idea on how to address this estimation problem in smaller blocks that are actually more manageable than the full block here. Okay? Here you see arrows, and these arrows basically means conditional dependence in some sense. Okay? So it means that for knowing the value of x, I need to know the values of u. And actually, if you see it from the inside here, for knowing the value of x, what I need is knowing u and knowing x at the previous step. Okay? And then I have some measurements here, this z, and this actually depends on the map and the position, okay? Which somehow intuitively makes sense. If I have a distance measurement, for instance, if I know how the map looks like, I know where I am, I can get a pretty clear idea on what I'm measuring in this distance. It would be like the meter, the 1.5, 2 meters away from the desk, okay? But if I don't know where I am, this measurement can be everything. Therefore, you have this dependent structure there, okay? We'll see then later on how this decompose the distribution, but just to give you an idea on how to use these models. Now, there are some grace variables like this. This means these are variables that I can observe. Okay, so it's something that I know, and information that comes from my sensors. There are white variables, in this case here, here, and here, which are the variables that I do not observe and are unknown to me. And then we have these gray boxes, which basically means these are the variables I'm interested in. Okay, so for full SLAM means I don't know the map, I don't know the robot path, and I'm interested in estimating both the map and the robot path. Now we have an online SLAM problem where it's basically the same graphical structure in behind, because the problem is the same, the relationship between the variables is also the same, but the difference is that we are only now interested in estimating the map and the last pose of the robot, but we don't care about the previous poses. So, and you can see it from here. Before we had all the path, and now we just have the final pose with all the measurements. Okay? Now, how do we go from one to another? As I said, most of the time, you can imagine this as estimating everything and then forgetting. So basically, we can say, if I know everything, so if I know my path and I know my map, I can just integrate out my variables. So forgetting from a statistical sense means getting the expected value of the variables that you're not interested in, okay? And this will basically mean computing a lot of integrals over the variables that I don't care about. Now, the point is, if you see it like this seems way more complicated than estimating the full trajectory. But the point is that you can do this recursively over time, and you actually do not really do this integral in a very complicated manner, but there are some family of distributions that allows you to just have some simple equations to update the state, and this update rule actually does this whole integral and some other things after that, okay? But in principle, you can imagine that this is the relation between the full slam here and the online slam there, okay? And basically, we can now restate the online slam problem in this way, where we know that this distribution is the integral computed out of these variables. Okay? Is everything clear? Yes, no, some question? Yes?
I have a question on how to read the diagram.
Mm-hmm.
Because it's a state X, to know the state X,
Mm-hmm.
you need to know the previous state
Mm-hmm.
and the control Q.
Yes.
But for that, it's not exactly the same way, because to know that, I either estimate it
Mm-hmm.
based on the map. Okay. No.
So I can maybe do it on a very simple example here. I'm not sure if this is going to be in the video, but so imagine very simply you have something like A, B, let's try to make it, and C, okay? And now I have something like this, this, and this. Now, if I want to know the distribution of A, B, and C, no? Like the joint distribution of all the variables I have there, this is equal to, you go from A, and there's nothing pointing at A, so it's just P of A. Then you have P of C, there is only A, C given A, and then B given AC, okay? So basically this defines you the independent structures of this distribution. Now why is this useful? Imagine now a simple discrete case distribution, no? So if you have a discrete distribution, this is like a table, okay? And this will be, imagine A, B, and C, they both have 3 different values that they can have something on, no? So this will be a table of 3 times 3 times 3, no? So these are the number of parameters you need to use to represent this distribution here. Now, if you look at this other one, basically this means that for representing A, I just need 3 parameters. For representing C given A, this will give me 3 parameters as well, because this will be 2 different things with 3 parameters, so there will be 3, and the same thing will be for the later one. So you need to have less parameters, because this one are actually given in this case, okay? So that's just how the thing eases up, and you have a better way of estimating the whole distribution. Okay, so it gives you a structure in your problem. Okay, does it answer your question? Okay, that's good. So,
in which cases the online SLAM is preferred to the normal SLAM?
It's a good question. So it depends how you which algorithm you use. For instance, if you use imagine that you use in this case. Okay, let's put it differently. You have here less variables. Okay, so if you do online SLAM, it means you only have to remember the pose of the robot right now. If you do the whole path, you need to remember all the poses. Okay, so from a memory point of view, if the robot is traveling a lot, your state always increases, and at some point you don't have enough memory for storing it, for instance. Okay, so in this case, it's better to focus on the online SLAM because you know that your state space, at least for the post point of view, is actually bounded, no? Because it's always one. And when you do the updates, basically you just take this, you do an update, so you actually increase, let's say, 2 level, so you will have xt plus 1 and xt, and then you do only one integral at the time. So it's always bounded and computed. Sometimes, and you will see it later on, when you consider the whole trajectory, it's actually sparser, and we'll see what sparse means. And for this case, then, for some algorithm, some solution, it's better to focus on the full path. Okay, but you can also do something in between. So you can also just say, I want to get kind of in between. I just care about the last 50 or 100 poses, and then whenever you have over 100, you take the 101, you marginalize out, and you keep on the fixed one. Okay. Further question? Okay. So I have a few other slides, but if you want, we can make a break now. I just have like 20 slides more. We can finish earlier or make a break, as we said before.
Finish early.
Okay. Fine. I like that. Okay. So why is the problem hard? And I hope I will give you an idea why it is. So we don't know the path and we don't know the map. Okay. So now let's assume that this will be the real thing, but we don't know that. Okay. And the map and the pose estimates are actually correlated. It means that if we change a bit in the map estimate, also the pose estimate will change. So they're kind of connected by springs, and you cannot move them independently. So if we get back on the idea here of independence, they are not independent, but they are correlated. So if you get now, for instance, initial measurement, you will end up that this is the uncertainty of the sensor. So we imagine we start here, and at least we know that the robot started in a certain location. Okay, so there is no uncertainty in the pose. There is only uncertainty in the measurement. So we know that the star is here with a certain probability around that. So this ellipsis gives an idea of the confidence area where the estimate is. Now we move, and the robot has some uncertainty in its motion. So we think that the robot is here, but it can be somewhere around this area. Now the problem is when we reobserve this uncertainty actually gets bigger. Okay. And the reason that it gets bigger, it's because you have to consider two sources of uncertainty for the map. One comes from the fact that I'm not sure where I am, and the other one comes from the fact because I don't know, I'm not sure about my sensor itself. And you can imagine that if this goes on and on and on, this uncertainty will always grow, grow, and grow. Okay? And in principle, the uncertainty of a landmark, you can imagine, can never be better than the initial uncertainty, and there are some conditions that can never be better than when you observe that. Okay? You then go on, and what happens is that you get a measurement of the same landmark, and since you're observing the same one, but from different sides, you can somehow shrink this and this and this. So what happens here is that, and that's also a matter of the correlation, that the uncertainty of this landmark got also smaller. And that's because everything is connected. By observing this landmark here twice, I know that the uncertainty of this landmark is smaller, okay? But since this uncertainty depends also on that uncertainty, also this uncertainty gets smaller, and therefore also the uncertainty of this landmark gets smaller, okay? So you will see this kind of magic happening, that you travel for a very, very long time, and at some point something that you observed, I don't know, 1 hour ago actually is more certain right now, just because you are more certain where you are in this specific moment, okay? And that's what the correlation does. So everything is connected, everything is depends on each other. Another problem is also that we have, so uncertainty also plays a big problem in that. And this is because we sometimes do not know if what we are observing is exactly what we think we are observing. So imagine that the robot is only able to see stars, okay? And now he has this uncertainty here, and it is 2 stars. Now I can either see these 2, okay, or you can see these other 2 here on the side. And both of them are actually valuable hypotheses from what he thinks he is on, okay? But only one of them is correct. So if you do a mistake, you basically will forever be wrong on where you are. And if you do instead the correct association, then you will be forever good in where you think you are. But you can also try to do something in between so that you still keep your uncertainty, okay? And that's a big problem. And you can see it in reality, like for instance in a city where there is a lot of Starbucks and you just go around blind, you open your eyes and you see a Starbucks. And now, is it the one in the station? Is it the one on main road? Is it the one which is in a small village close by? You don't know, okay? So, and that's the same problem here. So the more uncertain you are, the harder is this problem. So the harder is to decide if what you're observing is what you think you're observing, okay? And that's called data association. And that's a big problem in state estimation, especially with mobile robots. Now, this is somehow an idea of why is it hard. And now I want to give you an idea on how it's been addressed or what is a map. Because for now, we just saw stars and circle with a small line that was the robot. But so if you think about SLAM, there are several ways of subdividing the problem, okay? So there are something which is called volumetric approach. Volumetric approaches are trying to get an idea of the empty space as well as of the occupied space around the robot, okay? So you can see here a 3-dimensional volumetric approach. By the way, we are sitting up here. That's the building from that side, the 2 buildings. And you can see here there is a clear idea of the surfaces of the buildings. They are flat. There is clear idea of the empty space. That's the white stuff in the middle, and some poles and so on. So in this kind of representation, you have a clear idea what's an obstacle in front of you, what's free space, and so on. You can also do the same thing in a 2-dimensional projection, which is this kind of representation here, where you can see the white is free space, the black dots are actually occupied space, so where the walls are. This is a kind of blueprint of an indoor environment, and gray is places where we do not really know what's happening there. On the other hand, there are something called feature-based SLAMs, where they don't care about creating a full, dense, volumetric representation of the environment, but they just pick up some isolated points in the environment and they try to estimate their location and then also the location of the robot, which is much similar to what people have done at sea, where they were observing the stars and trying to build a map of the sky to be able to navigate overnight, for instance. And in this case, you can imagine this is something collected in Sydney, and you can see these individual dots. These are different tree trunks that a robot, where in this case was a car, drove around this park and detected these trunks and used that as potential feature in the map, in this case here. Okay, so these are two different potential approaches. Both of them are metric, so if you see it from a point of view of the robot path, it's roughly the same. So you have the same density of points, and it's all connected, and it's a full metric path. The only difference is the way you represent the map itself. But you can also have different representations. For instance, we can have topological maps, or we can have geometric maps, or also different level of details and of accuracy. This is a purely topological map. That's just I think it's the London Tube, I'm not sure. No, it's Paris probably. I don't know. It's somehow a map of the underground of some big cities. I think it's Paris, but I'm not sure. And this one is, again, a similar representation of a similar environment, but this is a metrical one. So here you can have all these measures of distances are actually accurate, but it might not be that the buildings are exactly where they are depicted on this map. No? But distances are accurate. Okay, so there are different map representation. In principle, as robotics, we are more often interested in volumetric representation. That's for two reasons. One is that they can give us an accurate location of the robot, but you can do it also with this kind of representation. And the second is that we can use them to do planning. Okay, so if I tell you the robot is here and I say I want to get there, he knows how to reach the place because he can actually plan a path in the free space. But if you use this kind of representation and I tell you the robot is here and I want you to get there, he has no idea that there are buildings in front of it that has to avoid, and maybe he has to go all around the neighborhood to come to that place. Okay? So, but if you just care about being localized very accurately, these are also valid maps as this other one here. Okay? Topological gives you a rough idea where you are, but you can still use it, but then you need to have a way of understanding kind of a semantics of places and so on, because here the only information you have is the name of the underground stops. So you need to have then a system that can read the underground names and recognize them and says, now I am at this underground stop. Okay, so according to the representation, we have different ways of also localizing and plan paths around that. A third interesting part and is regarding the taxonomy is if we have known or unknown correspondences. Okay, if you have known correspondences, the problem is way easier if you have unknown correspondences. And that's because of the problem I said you before, no? That you can have ambiguity, but if you eliminate ambiguity from the scratch, from the beginning, you say, these are IDs, they can be whatever, QR code that you can recognize with the camera, or they can be barcodes or something which is uniquely identified in the environment, then you know for sure the correspondences and the problem gets easier. If you don't, then you have an additional problem on top, which is the data association problem, and you need to be able to distinguish these two cases, if these two landmarks are these two stars or these two stars here. Okay? Again, a different level of complexity. Again, another problem is if you're looking at static or dynamic environments, because this creates an additional layer of uncertainty on top of the estimation problem, because now you don't know if you observe a displacement in your sensor data, if this displacement is caused by the robot moving or by the wall moving towards you. No? Because from a point of view of me observing the things around me, from the sensor view is the same. No? If I move or if everything moves with respect to myself is the same. That's the same effect you have when you are sitting in a train and you're just seeing the other train close to you moving, you look at the window, and you have this feeling that actually that train is staying still and you are moving. I don't know if you ever got this feeling while being on a train. That's exactly the same problem there, okay? So you need to be able to reason about things that you might know they move or not move, or about your internal state and your internal sensor, your odometry, saying, my other sensor tells me I'm staying still, so only the world can move and not myself, okay? So that's kind of the additional problem you have when you are in dynamic environments. Another problem is if you have small or large uncertainty, that we've seen it before. It creates, if it's in combination with the unknown data association, that can be catastrophic, because at some point you actually have no idea where you can be in this whole path. And according to where you think you are, you end up with a different environmental model, you end up with a different location of the robot, and so on. If your uncertainty is very small, you cannot make too much mistakes, no? And so basically here you go from expensive sensors, which are very accurate, to cheap sensors, which are also not so accurate, okay? So that's where the trade-off comes from. Another difference is also if you do active or passive SLAM. By passive, we mean someone is moving the robot around, and that person is deciding where the robot has to go, and the robot just collects the data and tells, this is the world, and this is where I am. Active means that the robot is not steered by anybody, and is making its own decisions on where to go. This might be more complicated problem because you put also some decision part inside, but sometimes can also be easier from the estimation point of view, because you can force the robot to go into places that help itself to get a better understanding. So like in places where the uncertainty gets always smaller and smaller and smaller, while if you let someone drive the robot, he might not know what's happening inside the robot, and he might drive it in very bad places, or maybe too fast, or in a way that it's the hardest for the robot to understand where he is, okay? In this class, we are mainly focused on passive SLAM, so we are not talking about the active part, but there was in Intro to Mobile Robots one part at the end called exploration, when there was a bit of a discussion how to do the active SLAM part. But if you're interested, you can ask me for material, I can give it to you, okay? Then we have computational aspects into the SLAM problem. So imagine that we have a limited time, so we really need to have a solution within a certain time bound, or we have a limited memory, so we really need to get a solution with a limited amount of memory. Or you can also imagine that we can, let's say, improve the memory by just changing the amount of RAM and using the same system to get a better and better result. So these are any time and any space problems where you try to get a rough solution with low memory and low computational time, but as long as these are increased, you can get better and better solution, okay? And this is we'll see something about this towards the end of the class when we will talk about hierarchical way of decomposing the environments and estimating in a more rough or high level point of view. And finally, we have the problem of if we have one single robot or we have multiple robots, okay? In principle, many techniques for a single robot can also apply to multiple robots. From a certain point of view, you can imagine that multiple robots are one single robot that teleports itself in different places of the environment. But if you want to do something meaningful in a distributed fashion, then things are a bit more complicated. You need to find a way of communicating part of the maps between different robots. You need to find a way of in each individual robot to be able to recognize where another robot is, or to plan, if you are on the active part, rendezvous point, something like the robot thinks that they should be close by and they just say, oh, let's meet, so we are sure that we are close by, and so on. We're not going to address multi-robot mapping in this class, but there is literature on that. Again, if you're interested, I'm happy to give you some material about that. You're almost done. So there are different approaches to the problem itself, and they've been developed in the last 20 years. The majority of the techniques are actually using probabilistic approaches or probabilistic, they have a probabilistic base on the solution. Some of them have been, let's say, maybe developed in a different way, but they still, you can find parallel to some probabilistic interpretation of the problem. All of them, in some way, tries to reduce the noise in the measurements. And whenever you have noise that you want to reduce, there's always a probabilistic model behind that can try to explain it. There are also some other problems in geodesy and photogrammetry, which are connected and slightly different. You can imagine photogrammetry, so for the people who do not know, geodesy is the science that studied the Earth, and photogrammetry is the science that study how to build maps of the world, kind of thing. They come from a different background, so the history is somehow like photogrammetry comes from the explorers that went around in the world and tried to draw maps of what they were seeing. They evolved, then they got also something called GPS, for instance, to get a better idea on where they are on Earth. So the problem is very similar. It's just that they use a lot of infrastructure that normally is not present for robots, or you actually do not, they are too expensive to put in use for the robots. One thing, for instance, is they have very high towers built on the Earth, and they measure with a very expensive optical system the distance and the angle between these towers. In the past, to measure the distance, they were really physically putting kilometers and kilometers of very thick ropes and cables in the ground, trying to have them as straight as possible and measuring how much of a rope was in between these two towers to get measurements. They also use nails in the ground, which are like that large or a bit smaller, with some codes, and they are able to see them either from airplanes or from satellite images to know exactly on the Earth where different points are. So you can imagine this is not something that you can do with a small robot that has to clean your apartment. It's a bit too expensive for an infrastructure in this way. But some techniques are related, and it's good to know that there is a long history on let's say, SLAM or mapping. And some techniques that we are going to use are actually coming exactly from photogrammetry. Like one, for instance, is the famous Cholesky decomposition of linear algebra. There was something which was kind of invented for this problem. I don't know if you know about optimization, like Gauss and so on. One of the reasons that this whole Gauss-Newton optimization algorithm was developed was to build the map of Germany and something like that. So there's kind of a nice history behind that. There is also an history of SLAM. Oh, this is not working any longer. Okay, I'll just go on. So there is also an history of SLAM written by a certain Durham White, who was one of the pioneers in the field. There is a paper where he talks about this whole history of SLAM. I can just tell you briefly that the problem started in 85, 86, where they tried to formulate how we can actually reason about this quantity, this space transformation in an uncertain way, and then goes on, and now in end of the 1990s and beginning of 2000, there was a lot of interest in the problem, a lot of papers in the research community, a lot of effort of a lot of groups worldwide. It was one of the most important problems at the time, and all the conferences were about that. Now it's getting a bit mature, so there's a bit of less, let's say, grounding results, but there's a lot of more advanced technical aspect as well. there are three main paradigms that we'll see in this class. There are, the first two are similar. They are a filter-based approach. Filter means that you are estimating the state of your system at time t only using measurements before this time. Okay? So you, in some way you cannot look into the future to know where you are right now. And the Kalman filter and the particle filter are two very known and widespread algorithms for doing filtering, or in another way, incremental state estimation. Okay? Graph-based approach is something that goes on a different point of view. We are addressing the full slam problem here, and we are doing in a batch fashion. So we just take all the measurements and we try to estimate all the poses and all the map. We have all the measurements, which basically means that the position of the robot at certain point in time in the past can actually be improved by considering the future observations. Okay? This is something that also happens in the Kalman filter through the correlation that I've shown you before, because everything is correlated. But if we have a nonlinear system as we have, the things are not exactly the same. So you can find, under certain assumption, that the full batch optimization and the incremental optimization are giving you the same result. But unfortunately, these assumptions do not hold for a real world with a real robot. So you can talk about them theoretically, but in practice, they do not hold. Now, what do we need as components? These are more or less the same thing that actually we had in the intro to mobile robots. We need this part here, which is the distribution of the pose at time t, given the previous pose and the control. Okay? This we call it motion model, or transition model, or evolution model. So it's the dynamics of our system. And then we have this other part here, which we call observation model, and it tells you what can we observe, given that we know the map and we know the pose of the robot. Okay? So in principle, we don't have it, we want to estimate it, but this is somehow a generative way of looking at things. No? You say, I have to model a way that connects, something that connects my pose and my map with what I observe. And doing it the other way around is very complicated, because you can observe, let's say, this distance everywhere in the world. But if you know that you are here and the world looks like this, it's just one unique way of getting you this measurement distance. Okay? And we will use this then somehow the other way around, and we'll see what it means to use them the other way around when we estimate the state. Okay? As motion model, we can write it like this. Again, the fact that we can remove a lot of the variables which are in here, it's because of the independence that we said. So we just care about these three variables when we talk about the motion model. And one example of motion model is, for instance, we have a Gaussian model. We are here. The robot moves, so we change the mean of the Gaussian, and there is also some noise in the motion, that therefore we increase the covariance of so the uncertainty of our position. But we can also have something which is non-Gaussian, so you can imagine here that the robot goes here and has this nice banana shape, and that's because uncertainty noise, actually they have a lever arm effect, so the further you go away and the further away you get from the uncertainty point of view, and you just see that there is this kind of moon-shaped arc. And you can imagine to represent distribution in terms of very fine-grained cells or fine-grained density. In this case, darker means the more likely. Or you can imagine them represented by a set of samples, as you can see in this part here, where each small black dot is a sample from the resulting distribution. No? And since at the end we are interested in knowing what's the likelihood, what's the probability of the pose being in a certain area, we can either sum everything up in a certain area here, or we can just count the number of dots in a certain area, and this this gives us an idea on what's the probability of the robot being there. Okay. So if you want to know a bit more on motion models, you can look at the chapter 6 of the Introduction to Mobile Robotics, or at the chapter 5 in the book. So there is one lectures on motion models. You can just have a look at the slides and at the recordings. I'm not going to go too much into the detail as it was in the Intro to Mobile Robotics, but this shouldn't take too much for you to get a refreshing or studying them. Okay. The second part that we are interested is the observation model, and now I just put it a bit more abstract. So X here is the pose of the robot, but you can imagine that we should also add the map for the SLAM case. And you can imagine this is just the state of the system, this is just the observation of the system. Okay. And this just relates what I expect to see if I am in a certain location and the environment looks in a certain way. You can imagine, again, to have Gaussian models. So I know this is my star is my map. Here is my pose. And I know that I have a certain mean distance, maybe mean angle, and a certain uncertainty around that. Okay, so that's how I can represent it. Or I can also represent it in a more sophisticated way with this mixer distribution that is made of different elements. Okay, so this here is a way of visualizing just a Gaussian around a certain level. Okay, so the way we put this ellipse is just a way of saying it's a two-dimensional Gaussian, and the ellipse is drawn at either 1 sigma. So if you imagine this is a Gaussian up to here, or 2 sigma or 3 sigma, and so on. Okay, that's just a way of visualizing it. Otherwise, we should have put a 3D plot of the two-dimensional Gaussians, and if you go in higher dimension, it's harder and harder to visualize. Okay. Again, you can look at the Intro to Mobile Robots, the set of slides after the motion models to get an idea on the observation models, and the chapter 6 of the book, which gets a bit deeper explanation on them. Okay, so we will use some of them in the lectures. We will use some other things later on when we're talking about graph-based LEM. I will try to get a refreshing before I use them in the class, but I think it's a good idea for you to get an idea on these models on your own during this time. Okay, so to conclude today, just try to give you an overview of these 3 words that are together, together makes the essence of this class: localization, mapping, and SLAM. And try to give you an idea on what's the different type of SLAMs, how we formalize the problem, what do we mean when we say online SLAM, what do we mean when we say full SLAM, and also give you a taxonomy of different aspects that are in the SLAM problem. We are not going to answer or address all of them, but just to give you a big picture idea on the problem. So as a literature for this, you can also get a handbook on robotics, which is a book that should be in the library. You don't really need to read too much about that, just the first subsections, or you can also get the probabilistic robots, and there is one small section that tells you what is LEM, but this is more on a general idea, and the slide suffices for that, so you don't need to have more than this. It's just how you represent it, the Bayes-net model, so the graphical model view, how you decompose this, and what it means in terms of the different problems, non-interassociation, unknown, uncertainty, correlation, and so on. If you want to get motion observation models, you can just go on the Intro to Mobile Robots or to the book Probabilistic Robotics. Okay, so that's all for today, and I'm now open for any questions that you have, both theoretical or organizational and anything. Mhm.
Did you take all the courses or there is some distribution?
If I'm gonna teach all of it,
All of it, or will Professor Bergard and you will?
so I will probably take most of it, if not all. I'm not sure. So we didn't really plan anything. So the idea initially is that I'm doing this whole class myself, and he will maybe help me with exams or doing some teachings where I'm not available. There might be cases where I have to travel to conferences or project meeting and so on, so there might be some other senior researcher students that will give you a lecture, or we just change exercise with lecture and so on. But I will be mainly myself. Any other question? Okay, so if there is no further question, we can also finish early as I promised, like 15 minutes early. And see you on Thursday then.